we define the limits of two variable functions in a similar way to one variable functions. And first we'll look at the informal definition. So if the values of a function of two variables are arbitrarily close to a real number L for all the points x, y that are sufficiently close to a point with coordinates x, c, y, c, then we say f approaches L as the points x, y approach point C. So we write this as the limit of the function of x and y as point x, y approaches the fixed point C. And that's equal to the real number L. Now if the point x, c, y, c is an interior point in the domain of the function, then x, y can approach this point from any direction. So we have multiple points x, y close to C that approach C from any direction as follows. And similar in concept to limits of one variable functions, for the limit to exist, we should obtain the same limiting value despite the direction that point x, y approaches the fixed point C. The epsilon-delta definition for two variable functions is similar to that of one variable functions. So we use the notation of the limit of the function of two variables as the point x, y approaches the fixed point C is equal to a real number as x, y approaches point C. So the function approaches the limit, and this is true if for every positive number, being epsilon greater than 0, there exists a corresponding number, delta, which is also greater than 0, such that for all points x, y, in the domain of the function, the distance between the points x, y and the point C, which is the square root of x minus xc squared plus y minus yc squared between 0 and delta, implies that the absolute value of the function minus the limiting value is less than epsilon. So we can interpret this as the point C being the center of an open circular disk, and this open disk has a radius of delta, and this expression on the right hand side as the function being within some margin of error of the limit. So we have L minus epsilon and L plus epsilon. And the distance between the function and the limit becomes arbitrarily small when the distance between these 2 points becomes sufficiently small, but larger than 0. So this definition applies to both interior points of the domain and also the boundary points of the domain. And the points x, y that approach a fixed point C are in the domain of the function. And this definition will become more clear when we apply it to examples. The properties of limits of two variable functions are similar to those of functions of one variable. So suppose we have the limit as the point x, y approaches the fixed point C of the function of two variables, which will take as L1, and let's copy this, and we have the limit of another function g being equal to L2 and r is a real number, then the following rules hold. So we have the limit as xy approaches point C of the sum of f of x and g of x is equal to the sum of their limits. So that's the sum rule, and the difference rule is similar. So the limit of f of x minus g of x is L1 minus L2. And the limit of the real number r multiplied by the function of two variables is the sum of the real number by the limit of that function. So we can take r outside the limit, and this applies to any real number. And similarly, the limit of the product of both functions, being f of xy multiplied by g of xy, is equal to the product of their limits. And similarly, the limit of the quotient of the two functions, so we have f of xy on g of xy, is equal to the quotient of their limits. So we can evaluate each limit separately and divide them together, provided the limit of g is not 0. And the limit of a function to the power of a positive integer is equal to the limit of the function raised to the same power. And we also have the root rule, which states that the limit of n root f is the same as n root L1, where L1 is the limit of the function. And it's the same thing as L1 raised to the reciprocal of n, where again n is a positive integer. So these rules help us to simplify evaluating limits algebraically. Continuity of functions of two variables is defined in a similar way to functions of one variable. So a function of two variables is continuous at the point with coordinates xc, yc if the function exists at that point. So f of xc, yc exists, and the limit of the function as xy approaches point C also exists. And the third condition is that the limit is equal to the value of the function at point C. So note that a function is continuous if it's continuous at every point in its domain. And the definition of continuity applies to interior points in a domain as well as boundary points. And for a function to be continuous, each point xy near point C must be in the domain of the function. And from the limit rules we covered, being the sum and difference rules, constant multiple rule, and so on, the algebraic combinations of functions, such as the function f plus the function g, for example, are also continuous at every point where these functions are defined. So if these functions are continuous, the resulting function is also continuous. If a function f of two variables is continuous at the point with coordinates xc, yc, then the composite function h equal to a function g of a function f being defined by h of x and y is equal to g of the function f of x and y is also continuous at the same point. So for example, suppose we have h is equal to sine of x plus y. So here we have the function of x and y being equal to x plus y. So this function is continuous, and therefore g being a function of one variable, which takes the output of f as an input. So note that f returns a real number. So that's equal to sine of f is also continuous. We can use the two-path test to determine if a limit does not exist. So if we have a function of two variables that has different limits in its domain, as x, y approaches a fixed point with coordinates xc, yc, then the limit of this function as x, y approaches point C does not exist. So for example, if we take a parabolic path and a linear path, so as the point with coordinates x, y approaches the fixed point, in this case being the point at the origin, and the limit of the function along these paths is different. So the function approaches L1 along the linear path and L2 along the parabolic path, then the limit does not exist. And this will become more clear when we cover some example problems. We can extend the definitions of limits on continuity to functions of more than two variables. So for example, if we have the limit of this function of three variables as x, y, z approaches the fixed point having coordinates xc, yc and zc. So given this is a real valued function that's equal to a real number, and also the continuity conditions for the function to be continuous at point C. The first continuity condition states that the function exists at point C, and the limit also exists as x, y, z approaches point C. And this limit evaluates at the value of the function at point C. And now we'll cover some worked examples. Let's evaluate the following limits. So with the first limit, we can apply the product rule. So we take the limit of e to the x and multiply that by the limit of sine y on y. So as xy approaches a fixed point with coordinates 0 and 0, we get e to the 0, which is 1, multiplied by the second limit, which also evaluates to 1, so that gives 1. And with the next limit, if we substitute x equals 1 and y equals 0, then we get the indeterminate form 0 on 0. So we'll try to apply some algebraic manipulation. So if we let u equal x minus y, then we can rewrite this as the limit as u approaches 1 of the square root of u minus 1 on u minus 1. So here we still have a limit of 0 on 0. So we can multiply by the conjugate. So we have root u plus 1 on root u plus 1. So that gives the limit. And we have u minus 1 in the numerator. And u minus 1 by root u plus 1 in the denominator. So we can cancel these out. And therefore, we get 1/2. And in this third limit, we also have an indeterminate form. So 1 minus cosine 0 on 0. So we can multiply this by the conjugate. So we have 1 plus cosine xy over 1 plus cosine xy. And we can rewrite the limit as 1 minus cosine squared xy, which is sine squared xy in the numerator, on xy by 1 plus cosine xy. So using the product rule, we can break this up into two limits. So we have the limit as xy approaches the fixed point of sine xy on xy, and that's multiplied by the limit of sine xy on 1 plus cosine xy. So the first limit evaluates to 1, and the second limit evaluates to 0 on 2. So the limit evaluates to 0. Let's show that this limit does not exist using the two-part test. So we'll try to eliminate x by taking y as a parabolic path. So suppose y is a constant by x squared, then we can rewrite this limit as xy approaches the fixed point. So we have x to the 4 minus c squared by x to the 4 over x to the 4 plus c squared by x to the 4. So factoring out x to the 4, we can cancel them out. And therefore, we get 1 minus c squared on 1 plus c squared. So for the parabola c equals 0, the limit evaluates to 1. And for the parabola c is equal to 1, the limit evaluates to 0. So therefore, as the point xy approaches the point 0, 0 along different parabolic paths given by c, we get two different limits, and therefore the limit does not exist by the two-path test. At which points are the following functions continuous? So here, we know that the natural log of 0 does not exist, so the function is not continuous at this point. So essentially the function is continuous at all points in the plane, where the point xy is not the point at the origin. Now for this second function, the value in the denominator can never be 0, because sine of x is restricted between minus 1 and 1. So therefore this function is continuous at all points in the plane. And for this third function, this function is continuous provided x squared plus y squared is larger than or equal to 2. So therefore the function is continuous at every point in space where this condition holds. So this means the function is not continuous where these points are in the interior of the cylinder with a radius of √2. Let's prove the following limit using the epsilon-delta definition. So recall for this limit to exist, for all numbers epsilon, which are positive, there exists another number delta, which is also positive, such that for all points in the domain of the function, that the distance between the 2 points, so we have x minus x naught squared plus y minus y naught squared, being between 0 and delta, implies that the absolute value of the function minus the limit is less than epsilon. So here x naught is 0 and y naught is 0, and the limit L is also 0. So starting with the function, we have the absolute value of x plus y on x squared plus 1 minus 0, and given the bottom term is positive, we can write this as the absolute value of x plus y on x squared plus 1. So this is the same thing as the absolute value of x plus y multiplied by 1 on x squared plus 1. So given 1 is always less than x squared plus 1, this is less than or equal to the absolute value of x plus y. And by the triangle inequality, that's also less than or equal to the absolute value of x plus the absolute value of y. So the absolute value of x is the square root of x squared, and the absolute value of y is the square root of y squared. So therefore this expression is less than or equal to the square root of x squared plus y squared plus the square root of x squared plus y squared. So that's equal to 2 by the square root of x squared plus y squared. So if we choose a number delta to be equal to epsilon on 2, then we see that 2 multiplied by the square root of x squared plus y squared, which is this expression, is less than epsilon. And therefore given our function here is less than this expression, which is less than epsilon, then the function itself is less than epsilon. And that proves that the limit exists. And note that we could have chosen different values of delta, but the definition only requires one value of delta.